Welcome back! In this video, we'll use reinforcement learning to master the game of Go. To play Go, you take turns placing stones on the board. The goal is to surround your opponent and control territory. It looks simple, but the space of possibilities makes it even harder to master than chess. In 2016, a computer program called AlphaGo beat the top human Go player in the world. This was a major milestone in artificial intelligence. AlphaGo is based on two big ideas. First, it learns from human experts by analyzing thousands of prior games. Second, it plays millions of games against itself, using reinforcement learning to get better and better. We'll start from the beginning. Where should we place the first stone? Let's consult the experts. Here are 3 games from some of the best Go players in history. You'll notice they all start in the upper right corner. But that's just 3 games. Let's download some others. And a few more. And here are 10,000 games played by Japanese professional players since 1941. Let's take a look at their opening moves. More than half of these games started with this move, and most of the rest started here. We'll show less popular moves as more transparent. Now suppose we chose to start here. Of the 5,514 games that began with that first move, here's the distribution of where White played next. Let's again pick the most popular one. We can use the same strategy to choose the next few moves. Cool! We've created a Go playing program. All you do is mimic what the majority of experts did in the exact same situation. But there's a big problem. After a dozen moves, we're down to a single matching game out of the original 10,000. It turns out Go games are a bit like snowflakes. No two are exactly alike. So memorizing prior games won't help you beyond the first few moves. We need a better approach to predict good moves. Let's train a policy that takes the state of the board as input and outputs probabilities for each of the 361 possible actions. Each of these actions corresponds to placing a stone somewhere on the board. AlphaGo uses a neural network that has 13 layers and trains on millions of moves from human experts. You can use this neural net to play complete games, and it's pretty decent. It can already beat most amateur players. That's cool, but to beat experts, the program needs to think more like an expert. Professional Go players can plan dozens of moves in the future. Consider this scenario. If you're White, you might think you should move here to keep Black from surrounding you. But then Black will go here. And then you'll have to go here to save your 2 stones. And if you play this out, eventually you'll lose all this territory. This pattern is known as a ladder. And it looks bad, right? But how bad is it? Well, suppose we simulate 100 different games forward from this state. White loses every single one. We say the value of the state is 0 for White. An expert can plan ahead to avoid bad outcomes like this. To see how this works, let's roll back to this point in time at the beginning of the ladder. Is this a good or a bad state for White? Well, if you simulate 100 games forward from this state, White wins 57, a value of 0.57. That's pretty decent. This value function gives a way to score states, and it's really useful for planning moves. Programs like AlphaGo plan ahead using search trees. This node represents the current state of the board. White moves next, and there's a branch for each possible move, from the top left to the bottom right. Black goes next and introduces more branches, and so on. Each path down the tree represents one sequence of moves. We only have time to explore a few of these paths. Which ones should we choose? AlphaGo uses 2 strategies to prune the search. First, it uses the expert policy we just trained to prioritize the most promising branches. These moves all have high probabilities. Second, it uses the value function to limit the depth of the search. The value function provides a likelihood of winning without simulating the entire game. You might ask, why search at all? Just choose the move with the best value function from the root. The answer is that the value function is only an approximation. It may not be accurate. So you're better off doing as much search as you can afford during the game itself. Value functions are super important. The more accurate they are, the more often your program will win. In these simulations, I use GNU-Go, an open source Go program. AlphaGo uses a much better approach for value estimation. AlphaGo starts with the move policy we trained from human experts. It uses this policy for only one player, white in this case, and a different frozen policy for black, whose weights are fixed. Now let's refine white's policy using reinforcement learning. This is just like we did for Pong in part 1. Use the current policy to play an entire game. If it's a win, all white's moves are reinforced. If it's a loss, the moves are penalized. AlphaGo repeats this approach, playing thousands of games against itself to improve its policy. And it will try out different opponent policies to gain experience playing against a variety of adversaries. Now we've simulated a bunch of wins and losses. We can use this information to calculate the value function. For example, this state had 2 winning games and 2 losing games go through it. So we estimate the probability of winning from this state is 1/2, whereas this state had 2 out of 3 winning games. But you'll notice most states aren't visited at all. How do we estimate values for unseen states? Well, we can do a lot more simulations. AlphaGo does 30 million. That sounds like a lot, but the 19 by 19 Go board has 10 to the 170th valid states. That's an astronomically large number, and it's part of what makes the game of Go so challenging. To generalize to unseen states, we'll use our old friend, neural networks. The 30 million self-play games gives us a lot of training data to train our value network. This is pretty cool. Think about it. Professionals gain experience by playing other people. You might play a few thousand games over the course of a lifetime. AlphaGo gets similar experience in just a few days by playing against itself over and over. This is the magic of reinforcement learning. To sum it all up, AlphaGo works in 2 phases. First, it automatically learns from human experts. Then it plays millions of games against itself, using reinforcement learning to get better and better. And just like we did with Pong in part 1, it's possible to drop the first step entirely and rely only on reinforcement learning. That's alphaZero, a newer approach from Google DeepMind that's even better. Stay tuned for part 3 to learn how reinforcement learning was used to train ChatGPT.